This is lecture 28 and we are going to talk about spectral analysis of explicit and implicit schemes. The specific content of this lecture is as follows. We will be first talking about how error propagates in convection dominated physical systems. That should set us up for requirement of high accuracy schemes, what exactly we want to do with that. And once that is discussed, we would move over and look at certain explicit central schemes. We will look at it from the physical plane point of view as well as in the spectral plane. The spectral plane will be indicated by the wave number k, and having done that, we would try to talk about upwind schemes. So, we will realize that many a times central scheme by themselves would not be adequate, and we would require some bit of numerical dissipation coming through upwind schemes, and that is what we need to represent, and we will find out what it is. Once we have done that representation, we will look at role of upwind schemes, what exactly it does, and we would notice that the role that it plays has a analog with the negative feedback that we have in electrical circuits. So, that is what we will show the connectivity of this concept with negative feedback stabilization of systems. Having done that, we have decided upon the schemes, whether we take central schemes with explicit numerical dissipation added, or the upwind schemes which has built in implicit dissipation. Next job in our view would be to really obtain the properties of numerical schemes, and in talking about the properties, we will be talking about the same three quantities that we talked about in the earlier lecture. That is, the first thing is the numerical amplification factor, its magnitude that we need to know about to ascertain whether the system is stable or not. Along with that, we need to find out what is the associated phase shift that comes about with each time step of integration, and that will bring about a numerical phase speed, which we have called here as C n. And finally, we would look at the group velocity, and the group velocity is one of the most important parameter that we need to characterize the speed at which the energy in the system propagates, and that is indicated by V g n. Okay. So, basically, having talked about the explicit schemes in the following, we would finally just set up some requirements should we decide to adopt similar high accuracy schemes in an implicit framework. So, let us begin by looking at the error propagation equation. To understand it, we once again resort to studying that one dimensional convection equation, which shows how the variable u propagates in space and time in one dimension, and c is the phase speed. And as we have noted in our discussion on waves, we have seen that this is a non-dispersive system. So, the energy also propagates with the same speed c, that also is the phase speed in this case. And having decided to adopt this equation as our model equation, we can obtain the numerical solution that we have identified here by u subscript n, and that we take a difference of it from the exact solution, and we call the quantity on the left hand side as the computational error. The numerical solution that we obtain, we could decide to express it completely in the spectral plane in terms of the wave number k and the circular frequency omega. That is one way of writing it. That is what we have done here. Or alternatively, we could write it in terms of those three parameters that we just now talked about, namely the amplitude of the amplification factor. And what do we mean by the amplification factor? That will be apparent when we look at the last equation. Amplification factor basically tells you from the Fourier Laplace representation that we have shown here. If we look at the Fourier Laplace amplitude at the advanced time step, that is u of k plus t plus delta t divided by u of k at t, that would be our numerical amplification factor. So, the first part of the solution is the initial spectrum that is given by the initial condition of the solution. That should be kept on advanced in time, given by the second factor, which is nothing but mod of g raised to the power t by delta t. T by delta t actually gives you the number of time steps that we have essentially taken, right. So, at each time step it amplifies by a factor of mod g, either it amplifies or attenuates. That would be determined by the property of mod g. And in addition, this complex g that we have written here would also give rise to a phase shift at each time step, and after n such time step we have arrived at t equal to t. That would give us a kind of a numerical phase speed that we have written here as c of n. And then we are basically in this equation E 3, we are representing the solution in a sort of a hybrid fashion, because the space x has been represented in terms of the wave number k, but the time is retained as it is. So, if we look at the expression that is given in the previous slide, we can immediately obtain the space derivative and the time derivative one at a time, and the expressions are given as they are. Please note that the fact that in the previous slide, the time dependence actually comes through the g term as well as the e to the power minus I k c and t term. It is for the same reason that when you take the time derivative, you end up with two sets of term in E 5. So, what you could do is basically use the definition of the computational error that we shown and try to set up error propagation equation. The idea is simple. If the governing equation is given by this differential operator on the left hand side here, so we want to see the error also does analogously the same thing or different. Please note, this is a linear equation given by the standard work done by previous researchers. It was conjectured that the error would follow the signal itself. However, what we are showing here, that if we represent E as u minus u bar n, then basically we will get two sets of terms in E 6, and you notice that this set of term is analytically is equal to 0. So, what happens is basically then the error is actually dictated by these two terms that comes about numerically. So, this is essentially the idea of setting up this error propagation equation. So, that is what we rewrite. If you note that in the previous slide, this right hand side had here c, and whereas as we mentioned in computation, what will happen is that c will be replaced by c of n, the numerical phase speed. So, that is why we have done this following manipulation. We wrote down the first line here in terms of c n, and in the second line we have subtracted it out, and this is what we get. So, essentially then what we can say is the error is governed by the left hand side operator, which is forced by the following set of terms that is on the right hand side. And since we know what the expression for u bar of n is. So, we can substitute those quantities, and if we do that in E7, we get this following representation here. Okay. So, one set of term depends on the numerical phase speed, the other set of term depends on the modulus of g, and look at the natural logarithm appearing over there. So, the last term that we had, last equation that we had, the phase dependent term, we can integrate by parts, and we can see that the equation furthermore simplifies in terms of this. You notice that naturally a term comes which is given here, which is nothing but d dk of c of n. So, this basically tells you that your original problem c was a constant, and what we are noticing here that we are providing the possibility that c of n, the numerical phase speed, need not necessarily be a constant. It could be a function of the wave number itself, and if that is so, that term would be contributed by this last term given here on this equation E9. So, basically we are looking at this expression, and we can substitute it back for this set of term in the error propagation equation, and we come out with this set of terms. And we notice one thing very clearly, that the first set of term that we have here depends on numerical amplification factor, and if the error has to be governed by the same equation as the signal itself, then we must have modulus of g equal to 1, right. So, what it actually tells you very clearly is that if you really want a well behaved algorithm, then you must have modulus of g equal to 1. Any numerical scheme for which modulus of g is not equal to 1 will contribute to forcing of error through this term. Okay. And the second set of term tells you that your numerical phase speed is going to be a function of the wave number k. If it is so, that also will give rise to additional error, and this property where c of n is a function of x, function of k, is an attribute of a dispersive system. If c n was not a function of k, we would have called it a non-dispersive system. Our original equation was a non-dispersive equation, because there c was constant. But here numerically we have converted a non-dispersive system to a theoretically a dispersive system. Now, individual algorithms will provide us an estimate for modulus of g and the expression of c n, and from there we should be able to find out whether the method is the right one in terms of the error due to instability or stability, or error due to dispersion. Okay. So, having laid this groundwork, we can now state what exactly we really want to do if we want to perform high accuracy computing. First and foremost, we agree that what we require, that any space and time scale that is relevant for the physical problem, they have to be resolved, right. So, the first term is very obvious. We need to resolve all physical time and length scales. Now, the second term is what I just now described to you, that we need to have mod g equal to 1. That means, we need to have a neutrally stable system. We cannot have instability, of course, then the solution will blow up, you will immediately know, but what is not always realized, that you cannot also have so called stable dissipative system. The basic idea is the following, that numerics should not impose its role on the physics of the problem. So, numerics should stay neutral, physics should dictate whether the system is stable or unstable. So, that is why numerically we do not want to add any dissipation. This is absolutely unwarranted. Now, we also seen in the previous slide that there is another source of error, that is where the numerical phase speed becomes a function of wave number, and we said that is a hallmark of a dispersive system. We do not even want that, and that is what we have stated in the point 3, that each and every wave number component should propagate its phase and energy at the correct speed, and that I have stated to you, that is the group velocity. So, we will go ahead and figure out how these things are evaluated, and we will find out how to avoid spurious dispersion. Okay. So, that is that. These are the 3 prime requirement of high accuracy computing system. Next, what we also realize that when we are replacing a differential equation by its discrete version, we are essentially indulging in some amount of truncation of terms, and that error is what is called as a truncation error. It has become quite commonplace for anyone and everyone to look at the property of the numerical scheme in the physical space, and then people try to talk about the order of the discretization, and it is hoped that you have a higher the order of the discretization, lower will be the error. However, this is somewhat misleading, because the error of course behaves like this. Suppose I have a nth order system. So, that would be given by a term which will be dependent on the order of the system, and there could be probably say n factorial term coming in there, and then what we could have is that we will have say associated higher derivative term. What is basically done in most of the time when you look at higher order accurate system, you are basically talking about this term. You expect that if this exponent is high, delta x being small, the contribution will be small. But the essential point remains that what we need to look at is a basically product of the two. It may so happen that I have n equal to 6, then this is okay, then I am looking at this, but I can derive another scheme where I would have a term here which is, let us say, instead of 5 it becomes, let us say, 2, but then the associated term there would become, let us say, the third derivative, and for that particular physical problem the third derivative could be much lower than this quantity. There is no guarantee that higher the order of this term, lower is the magnitude. In fact, in most of the physical system it happens the other way. If you look at the higher order derivatives, they also carry higher amplitude. This you can very clearly understand if you look at a term like this, and if I write its Fourier representation, then I would be writing like this, and if I try to figure out its nth derivative, then what I am going to get would be nothing but I k raised to the power n and u of k e to the power I k x dk. So, you can see higher the n, of course, you are going to get higher contribution coming from higher wave numbers. So, this is quite easily understood that this route of characterizing schemes by order of the term in terms of the grid spacing is erroneous. What instead one should look at its representation in the spectral plane, if the neglected term is negligible or not. If it is negligible, you are done. So, we are going to take that kind of an approach, and what we see that many a times that you could derive schemes which are formally lower order, but they are truly higher order from the perspective of its behavior in the spectral plane. Now, let us explore this for some simple example. For example, let us say we are interested in discretizing the first derivative term, and that is important in many physical systems. So, let us begin with the first derivative. Suppose we perform a second order central difference schemes that is given by equation 1 here, and you can see that it is related to its neighboring point I plus 1 j minus I minus 1 j divided by 2 h, and the highest order truncation error term is proportional to h square by 3 factorial, and this is the third derivative, and rest of it is order 4 and above. The same way we can also obtain a fourth order scheme that would involve more number of points. The essential point that you notice that migrating from a second order scheme to a fourth order scheme, your stencil size becomes bigger. For example, equation 1 involves 3 points, equation 2 involves 5 points, and if you look at the corresponding sixth order system, it actually involves 7 points. This is the essential feature of explicit scheme. You want to go higher order, your stencil size increases, and we will talk about why this may not be always good to go for higher and higher order schemes. Now, if I want to view these central schemes in k plane, then what I can do is I can represent a function, let us say f of x and t in this hybrid manner, retain the time dependence as it is, and introduce k instead of x, and then we perform this integral. If we use a uniform grade, then what we usually do is we represent the second derivative like this, that we just now seen. And if we now substitute 4 in equation 5, noticing that x is equal to m times delta x, then I would get the Fourier amplitude retained as it is, and in the phase I will write e to the power I k m plus 1 delta x minus e to the power I k m minus 1 delta x. And you notice that e to the power I k x is nothing but e to the power I k m delta x. Okay. So, what happens as a consequence? We get an expression for k equivalent. Let me explain what this k equivalent is. If I represent u of x and t in terms of u of k and t e to the power I k x dk, then del u del x can be very easily written as I k u e to the power I k x dk. So, this is your exact representation, right. And what we just now seen that numerically what we got? Numerically we got u of k retained as it is, and we had obtained e to the power I k delta x minus e to the power minus I k delta x by 2 h, and then we had e to the power I k x, that was m delta x, right. That is what we say, that is our x, and dk. So, what happens here? This is your numerical representation. So, what you are noticing that in getting the exact representation, what you did, you had the Fourier amplitude, you just simply multiplied by I k to get the derivative, right. So, if I look at this, I could write this equation also in terms of u of k as it is, and this quantity that we have here, let me write it as I k equivalent. Okay. And then we have e to the power I k x d k. So, what happens? You see, doing the numerical operation is equivalent to replacing I k by I k equivalent, right. And what is this I k equivalent? I k equivalent is this quantity, and what is this? 2 I sin k delta x, right, by 2 h. So, that I will get equal to I sin k delta x divided by, well, I am mixing up. So, instead of h, let me write this as delta x. So, I am going to get this as equal to I k delta x by delta x. Okay. So, what happens is then of course, you can get rid of this, and then this is an expression that we have derived it for CD2 scheme, right. So, what we are going to write here as k equivalent by k for the CD2 scheme is going to be sin k delta x by k delta x. Okay. So, we can carry on with this exercise for CD4 and CD6 scheme, and what we notice is that we can get some expression for k equivalent by k for CD6 scheme given by sin 3 k delta x etcetera, etcetera. That is given by your equation 8. So, we are collecting expressions for this in the k plane. Now, let me tell you about a method that was developed here a few years ago, where we actually wanted to develop a 9-point schemes. So, we want to explore a 9-point scheme, but what we wanted to do was we wanted to optimize the scheme, so that the error of this 9-point scheme is much lower than many explicit schemes. So, basically what you do is what I have written down in this equation A, that I will write the dul dx, that would be a naught by 2 h, and you can see the terms appear pairwise. Terms appear pairwise. For example, L plus 1 and L minus 1 are coupled together. The same way L plus 2 and L minus 2 terms are coupled here, and you can see that without the presence of UL we have 9 points there. Now, how does this scheme behave, or how we go ahead and do it? That is what we are going to see, that we have written down those expression in the physical plane. Now, what we could do is, on the left hand side we have du dx, on the right hand side we have those 9 points. So, we can write down the Taylor series and match term by term, and when we do that, we are going to get various odd derivative terms. Even derivative terms will all become 0. Why? Because you can see that the way these terms appear pairwise with a minus sign in between. So, if you do a Taylor series, this will only retain the odd derivatives, all even derivative terms drop out, and then you successively sort of equate the odd derivatives, all kinds of derivatives on the left and right hand side, and write everything in terms of one of the parameter. Here we have used a naught as the parameter, and matching the Taylor series we get expression for b naught, d naught and e naught in terms of the parameter a naught. Okay. Now, what we want to do is, as we have seen here, first derivative is given in terms of I k u for the exact quantity, and for the numerical quantity is I k equivalent u. So, the error would be difference of the two, and that is what we have written in this equation C. If you look at equation C, that is the error, the difference between exact and numerical estimate. Now, what you could do is, of course, we have the expression here, and we can use that. Okay, use that in the expression for the derivative that we have written there in the previous slide, that what we can see here given in this equation. And so, what we could do is basically we could substitute that Fourier Laplace series, and we will get this expression that we have indicated here. Okay. Now, your problem is set. You have the expression in C that is going to be a function of what? Only A naught. So, what we did was optimize this error as a function of A naught, and we have done two things. We have taken u of k equal to 1, that is true for delta function excitation. Okay. That is the most conservative estimate one can get, and the other thing is we did not go the full limit from 0 to pi. Instead, we have taken a limit which is slightly lower than pi. Okay. In performing this optimization in equation C, we end up getting a value of A naught. Okay. So, we have now introduced some schemes here, and they are essentially plotted here. What you are seeing is a host of method. The purple color is the CD2 method that gives you that k equivalent by k. It is the performance parameter, right. Ideally, we want it to be equal to 1. And what we are noticing here, that CD2 scheme falls off from the ideal limit for a very small value of k h itself. What is k h? K h is nothing but non-dimensional k. K is a wave number. Its a dimension is 1 over length, and h is delta x, which has a dimension of length. So, k h is non-dimensional, and that we have shown it in a limit of 0 to pi. Okay. Now, once you see that, you notice that we have shown here the CD2 scheme. CD4 scheme is shown by the green line, which is shown here. UD3 is a third order upwind scheme, which we are going to subsequently define, but please take a note at this SS scheme that we just now obtained as a optimization exercise, and you can see its performance. It is 9 point, it is a 9-point formula, but what happened in getting those conditions for Taylor series, we actually have matched up to 6th order. So, basically it is a 9-point, but it is 6th order scheme, because that is how we matched the Taylor series, because we kept A naught floating. However, this k equivalent by k that we have plotted here against k h, this performance parameter is better than if you would have taken a CD8 scheme, because that is what we want to do, because you have taken a 9-point, and what you really want is a benefit that is more than that you could get with a CD8 scheme. And that is what we mentioned, that you should not focus your attention in the physical plane. Instead, you should look at in the spectral plane, and that is what we are seeing. In the k plane, this nominal 6th order scheme performs better than an 8th order scheme, and this is basically an explicit scheme. I have purposely drawn another line here, which is shown here by this black line. This is an implicit scheme that should motivate us to look for them, and as it appears here, that this implicit scheme is far more accurate than this explicit scheme. We are going to talk about it as we go along. Okay. So, now if I try to see its usage, for all this derivative operation, we want to compute a real flow at high Reynolds number. If we use the central scheme, it may not work. Because what happens is the properties, combined properties of the space-time discretization will show that such schemes, central schemes, are susceptible to very high wave number error. So, you need to stabilize your numerical method against those high wave number error. One of the way of utilizing upwind scheme is to introduce numerical dissipation that prevents numerical instability. This is the motivation for abandoning explicit scheme and instead going for upwind scheme. Explicit central scheme will be abandoned in favor of explicit upwind scheme. And we have to be careful, because we have already seen in the derivation of the error evolution equation that in our GEAL, if we want to make the method stable, we can also introduce error. So, that is what we have to be careful, that even stable algorithm creates error. So, we will have to worry about it, and that is why we have said very clearly that we need numerical stable algorithm, right. And so, if taking upwind scheme is an absolute must, we have to be rather careful in adding just the right amount of dissipation, which will take away those high wave number errors, while it should not tamper with the physical nature of the problem. That is what we want to make a comment here, that we do not want to make the system overstable. That is something we must be careful of. Okay. So, what does upwinding does? Again, let us try to explore it with the help of our model equation, that convection equation that we have shown here, del u del t plus c into del u del x. Now, let us take one of the simplest possible upwind scheme. You have noticed that all central schemes are even ordered. Okay. We have looked at the CD2, CD4, CD6, etc., where the stencils were symmetric, and we always ended up having even ordered scheme. So, if we look at the first order scheme, then what happens? Let me explain this somewhat better, because we are looking at a problem where our governing equation tells us that the signal is propagating from left to right, because C is positive. So, if I give some kind of a initial condition in the xt plane, and if I give some kind of a initial solution like this, what happens with the passage of time? This condition will move to the right. So, at a later time, I might see that this solution has moved here. This is the property of this equation, that it does not amplify or dissipate, and it also does not disperse. So, if I have a packet like this, the packet is retained as it is. Okay. So, what happens if I try to solve an equation like this using first order upwinding scheme? That is what you are noticing here, that I have purposely looked at the del f del x at the mth node. So, where is the information coming from? It is going from left to right. So, what I should do is, I should write an expression which should involve the mth node and with the m minus 1th node. So, this is what we are going to do. We have an expression for f that we have seen in terms of Fourier Laplace series. That is what we have done in equation 9. Okay. So, we just now seen that if we follow the physical nature while discretizing through the equation 9, we are actually following the correct trend, because information is propagating from m minus 1th point to the mth point, and that is precisely what we need to do. And again, using the Fourier series, Fourier Laplace series, what we can see that we can work out the k equivalent by k. You can work it out, and what you would notice that it has a real part which looks exactly like what we had obtained for the CD2 scheme. In addition, you have an imaginary part. The imaginary part actually is the numerical dissipation that we have added to the scheme. Okay. Why I am saying numerical dissipation, which we can show it subsequently, but what we can do is basically having obtained this scheme here del f del x. So, what we could do is basically if I am writing this, I will be writing here u, we are looking at the mth node. So, I will be writing here like this u m n by delta t. So, this is my Euler time integration for the time derivative, and then I will be adding c u m n minus. Now, we are doing first order upwinding, right. So, that is why I am writing it like this. So, I can write down the Taylor series, the Fourier Laplace transform, and then what we are going to do is we are going to write, if you remember, we have introduced that as u of x m t n, we have written it like u of k t of n, we will write it as e to the power I k x m d k, right. That is our expression, Fourier Laplace transform expression for the variable. So, I can substitute it there. So, what we are going to get is basically from here I will get u of k t n plus 1, and from here I will get u of k t of n, and this is divided by delta t, and c, what am I going to get here? What I have just now written here. This is the expression that is given. So, what we are going to get? So, this whole thing that we are writing comes under the integral sign. We are performing integral over all k, and so here I am going to get c by delta x, and what do I get? Here it will be 1 minus e to the power minus I k delta x into u of k t n. This whole thing I am going to multiply with respect to this, right. So, that is what we have written here. So, it has been multiplied by e to the power I k x d k. So, since this whole thing is equal to 0, the integrand must be 0. So, what we have done essentially then, we have basically then say that the integrand itself must be equal to 0, and that is what we are going to write equal to 0 as. Now, if I divide this equation by u of k t n, then this term will give me g. That is the definition of g. Remember, g of k t n is nothing but u of k t n plus 1 by u of k of t n. So, if I divide this equation by u of k t n, then what we are going to get is the following. We are going to get here g minus 1, and if I take this, what do I get? C delta t by delta x is our CFL number. So, that is going to be our CFL number NC. Okay. So, this is a well known CFL number which we have talked about many times before. So, we are not surprised, and in addition we are getting here 1 minus e to the power minus I k delta x. 0. So, you have an expression for G. Okay. So, what we do is, having obtained the expression for G, we can plot it. And this plot is a very fascinating plot, because it says very clearly that you have a vertical line corresponding to n c equal to 1. To the right of that line, the method is unstable. Everywhere G is greater than 1. So, there is absolutely no mystery here, that if you are adopting this method, never try the value of n c greater than 1. If you do take n c less than 1, then you can see that for different wave number are going to be attenuated by different amount. Higher the value of k h, higher is the attenuation. Whereas, if you take n c exactly equal to 1, what you are getting? G is equal to 1 everywhere, and that is your exact solution. So, what we have learned, that upwinding by itself is not bad, provided you do it physically, and here doing it physically is equivalent to taking n c equal to 1. So, you understand that there is nothing wrong with upwinding per se, but if you overdo it, say instead of taking n c means what? It is a measure of c times delta t. So, delta t, it basically tells you a time step that you are taking. So, if you take a time step which is too small, then you do not get generally more accuracy. Here it shows very clearly, to get the maximum accuracy, you will have to take delta t is equal to delta x by c. That means what? Every time step your solution is travelling by one node, and that is the definition of phase speed c. So, you can very clearly appreciate what has been achieved here, that you do get exact solution for n c equal to 1. If you take more than 1, you are unstable. If you are less than 1, it is stable, but it will be erroneous. Then we can plot this C n by C. See, basically what we have written down here, G as given here. So, this could be written down also in terms of like a modulus of G, that is what we plotted in the previous slide, and then we can also get its phase, which I write as beta j. What is beta j? Beta j is given by tan beta j would be nothing but G is complex, right. So, G is complex. So, we get G imaginary by G real. So, I get this. So, what does it mean? That whenever I am actually numerically integrating, I am amplifying or attenuating by mod G, and the solution is shifting its phase. That is what it is doing, it is moving to the right. So, every time step I need its phase to shift, and that numerical phase shift is given in terms of what you have gotten the value of G as. Now, once you have gotten the value of G there, and in consequence you have gotten the value of beta j, we have shown it already that beta of j is nothing but equal to can be related to C n by C. So, C n is the numerical phase speed that we can show that C n by C will be beta j by omega times delta t. Okay. So, once you have obtained beta j, you can calculate numerical phase speed. So, they are all related. So, the basic task is choose your numerical algorithm, obtain the value of G, collect its real and imaginary path, obtain C n by C. The same way you can also get your V G n by C, that should be equal to 1 by C delta t d beta j dk. This is what we have discussed when we are talking about hyperbolic equation. What you notice here is in this C n by C contour plot also a beautiful thing, that for n c equal to 1, you have Cn by C equal to 1. That is exactly what you want, that should be equal to 1. Numerical phase speed should be equal to the physical phase speed. Well, it is rather interesting that even for a value of n equal to half also you get the same quantity, but we have seen in the previous slide that there you will have G property that is not desirable. So, we notice that, and the same thing you can look at in terms of the group velocity also. The Vgn is exactly equal to C, what it should be for n equal to 1. So, this is essentially the idea by which we can really work out. Now, let us look at the consequence of this UD1 scheme. I told you that K equivalent has a real part and imaginary part. So, that is what we have written down here in equation 11. We have shown it, the real part gives rise to this, which is like your CD2 scheme that we have noticed before. This imaginary part actually gives you a added dissipation. Why? Because on the left hand side I have this term. Now, if I have some quantity, a positive quantity with a negative sign, I put it on this side, then I am going to get this term. That is what? A positive quantity k I square, right, k I square times f. So, this actually plays this role. If you have the Fourier Laplace transform representation of a function, you do it take the second derivative twice, then you end up getting an expression of that kind, minus k square u of k. So, this is exactly what has been achieved. It is a rather interesting thing that to get a solution which is numerically correct, we added up some numerical dissipation which was not there, but we have chosen in such a way that delta t and delta x in such a way that we have kept n c equal to 1 and we have achieved a perfect solution. So, basically once we have made this case for first order upwinding case, what we have shown, if I look at the first order upwinding case, that first order upwinding case is equivalent to doing this here. This is your CD2 scheme on the left hand side, and to that you have added a second derivative term, that is your first order upwinding. So, we can generalize it. Say for example, we generalize it to a third order upwind scheme. So, third order upwind scheme will be, I will take the derivative here, a fourth central difference scheme, and to that I will add a fourth derivative. That is your third order upwind scheme. You can successively generate fifth order, seventh order scheme, so on and so forth. So, where we can now already have seen what del f del x CD4 expression is. Here I have shown you what this fourth derivative expression is in terms of that, and if you substitute all of that together, your del u del x by third order upwind scheme is given by equation 15. Okay. So, this has been done for a case where the signal is propagating from left to right. Okay. Having done that, we have the Fourier Laplace series and we can substitute it, and we will get the real part of k equivalent by k for UD3 will be exactly same as CD4. In addition, what we will get? An imaginary part, and that is what is shown in equation 16. So, one can work it out and one can see that third order upwinding is equivalent to adding this term, and this is what you get to see if you plot all the k imaginary by k, plot against k h. If you look at all central schemes, they all fall along 0 line. These are what you get for all the central schemes, whereas this brown line is for first upwind scheme, and this is your third upwind scheme. What you notice, interestingly enough, that there is a qualitative difference. Third order upwind schemes start become active at relatively higher wave number whereas first order upwind scheme become active right from the beginning. So, what we could do is we can try to rationalize what upwinding is doing. Upwinding, let us say we look at some kind of evolution equation like this, then we can think of L of u includes all the spatial derivatives and we can represent it. And then what we could do is we can write down the spatially discretized scheme like equation 18. And you see there are all kinds of terms involved here. K goes from 0 to n determined by the order of the scheme. We have seen that if we take a second order scheme we need 3 points, if we take fourth order scheme we need 5 points, if we need sixth order scheme we need 7 points. So, n is determined by the order. And what we have done a similar analysis for space time dependent equation and we can work it out in that particular fashion. So, basically the discrete equation what we really need is it should be stable, but what we find that central schemes are neutrally stable, because just now we have seen that k equivalent by k imaginary is 0. So, it does not add any dissipation, it is neutrally stable. But if there are numerical instabilities at high wave number due to some high k source, then we need to suppress that. Okay. What happens in case of a central scheme? You always see oscillations with wavelength 2 delta x, and this is the highest wave number that you can resolve with that grid. If I have grid points like this is the smallest wavelength wave that I can represent, right. So, that is what we are seeing. So, the oscillation is related to 2 delta x. Now, if I write down the corresponding error equation, which is not very trivial, to control this oscillation at 2 delta x, what we really understand that the central schemes are insensitive to the node point we are looking at. However, if I do upwinding, I notice that the schemes as we have seen here, if I am looking at the mth point, there is a term here which involves the mth point itself, which is not there in central schemes. So, whenever you do upwinding, you get this term, and when you get this term, you actually can write down the error equation which will involve this term. So, that means the error at the Lth node is coupled to the error at the Lth point itself, and if suppose p is 0, I could integrate it and I can show that E of L goes as e to the power alpha t minus exponent. So, if alpha is positive, then this is going to show that the error is going to decay with time. So, that is the whole key to stabilizing schemes, that you need to add a term in such a way that it provides this minus alpha of this kind, and this is what exactly you decide by this. Okay. So, I suppose you can get some of these plots as it is shown here, numerical amplification factor for some of the schemes CD2, CD4, UD3 and this SS schemes that we have talked about. Same way we can work out the expression for Cn by C, and we can work out the expression for Vgn by C. So, this is your phase speed representation, and here you have the group velocity representation. What you notice is certain properties which we will be exploring once again when we talk about compact scheme in a later time. Okay. So, I think I will just stop at this point, and we will get back to a framework where we will be talking about compact schemes, which are essentially implicit schemes, which perform some of this task that we have set up today in a better manner. That is what will be taken up from next lecture onwards.